Today I'm going to talk about the emergent quasi-particle of spin 1 trimer chains. Here is my plan of my talk. I'll try to motivate because these models are generally very boring. So many people will say, okay, what is your motivation? So I'll try to motivate you and try to give you some examples like spin half. Start with the spin half trimers, especially the alkali-based copper germinates, which is already synthesized, and in fact the experiments are done and they have observed different quasi-particles. So again, I'll discuss briefly about the physics of excitations in spin half trimers, and then I'll try to talk about what is the difference. In fact, well-known one-dimensional system, if it is of spin half and if it is a spin 1, what are the differences? And then I'll come to the talk about what happens to the excitations in spin 1 trimer and how it is different from spin half half trimer excitations and their quasi-particles. And later on, at the end, if time permits, I'll also try to comment about what kind of materials exist right now for this kind of trimers and what we are looking for. Okay, so with that, I'll start with this first example. So this is sodium copper germinate, and it is a 3-dimensional system. You can see here. If you go along this, you see that it looks like it's a 1-dimensional chain because it's separated by the sodiums. Sodium will keep these two chains very separated out. Okay, but if you see more carefully, you'll see that there are 3 coppers which are very close together, and the next one, and that's why it forms the trimer. And if you see the next trimer, it's mediated by germanium and oxygen. So the distance is quite a bit high. So these are sort of weakly interacting. And we are interested in the magnetic properties of these systems. So these coppers are the main, playing the main role. Okay, and all of us know that these coppers will have spin half, right? Effective spin of this system will, for each copper, is going to be spin half. And okay, so if you see this, this compound is synthesized by the Professor Yusuf's group and Professor Anup Bera's group from BRC, and then all the measurements are done by them. I'll come back to this model again. Before that, I want to show the other examples of the trimers. If you see this azurite compound, there are many variants of these azurites, and many of those shows this kind of structure. If you see, right, if you confine in some particular C direction, hopefully B direction, and you'll see this kind of like a change. So these are trimers, right? And these shows very interesting. If you see the MH curve, you'll see this plateau, magnetic plateau. Magnetic plateaus are always interesting because there is some topology in it, right? And also this this plateau corresponds to that you have a energy gap at that particular magnetic ground state. Okay, so here are the other materials. If you see that this lithium copper molybdenum oxygen, here the copper is only like contributing for the magnetism, and these are actually triangulars in nature, but still the dominant physics is governed by these trimers. And in fact, what we observed in this, that these systems, they can be 1D or 2D, trimers are playing the main role, but these weak couplings also for low energy physics, this is very, very important. Okay. So again, let's come back to this sodium copper germinate. This is very well studied experimentally as well as theoretically. So if you see this, there are we can make a model for this for 1D chain. Here these trimers have like a strong exchange G1, and then it is 2 nearest neighbor trimers can be coupled with very weak coupling J2, and within the trimers there are other coupling J3, which is very small. These are actually J2 and J3 both are small, and by using the fitting of the experimental data, neutron scattering, magnetic susceptibility, or specific heat, if you do that, and it is done for this paper, then you find that your J1 is 235 Kelvin, and like J2 and J3 is roughly of 42 Kelvin. Okay, so what is interesting here is how do you distinguish it from the this in energetics. So if you're going to the full chain, let's consider only simple trimer. You have 3 spin half. So total number of degree of freedom, how many you have? 2 to the power 3, so 8, right? And if you take this simple Hamiltonian for the trimer, then you can actually get all the excited state, all possible excited state. What you find is there are 4 doublet state, and these doublets, there are 4 types, but 2 are low in energy. The reason is this forms like a singlet bond to the 2 outers and 1 mid, right? A linear combination of that, and up and down is your the other degree of freedom. So basically, at the end of the chain, you always have effectively spin half, and that makes it lower in the ground state. So, and higher excited state doublons or doublets are where mid spin is free. So it is locked between the 2, like singlet formation between the edge spins. So this spin half gets locked, and then you energetically it's a much higher. And the next 4 states are the cotton states, or spin like a your 3/2 spin, right? I mean, because all are ferromagnetic aligned, spin becomes 3/2, and you have a 4-fold degeneracy of that. And because of the degeneracy, we have given the name because these are excitons, right? I mean, ground state is only low-lying doublons, and the next one is excitons. So we can think in terms of the quasi-particles and say that this have a spin half, so you have a doublons, 2 degree freedom doublons. If you have spin 3/2, you have a 4-fold degeneracy, so it's quadron, and that's how it has been named in literature. So we followed that, and you can see that these are the neutron scattering, like a structure factor you can get, and this is your like what they have observed here. Here you have experimental, this is theory, and this is very good match. Okay, let's not get into too much of this because today we are not interested in this compound. So basic idea of this spin half and integer, spin half integer and integer is given by the Hall, and he said that if you have half spin system or chain of half spin system, their spectrum is going to be gapless, okay? And if it is integer, right, spin 1, 2 or 3, these are the spectrum is gapped. The ground state of the spin halves are quasi long range order, so it's still not a like a ordered system, but it's a quasi long range order, so it's a sort of like a quasi ordered state, I would say, right? And then if you take the spin 1, what you find that it forms a VV state like structure. So you have each of the spin 1 can be divided into 2 spin halves, and these couplings, these 2 spin halves couples into ferromagnetically forms a singlet like structure, and at the edge you have 2 like free spins. Okay, so if you put the bonding condition, I mean periodic bonding condition, this spin 1 will go, but effectively what it forms is this VVS state, and if you want to excite anything, you have to break these bonds, and that's how the gap develops, right? And that's why the spin 1, whenever you see the magnetic susceptibility, it will you'll see that it's a gap, so your magnetic susceptibility is 0 for quite some time, and then it rises exponentially. Okay, so because we are interested in this trimer chain of spin 1, so what we should see that this should be like, if it is a normal chain, what we would have expected, this should be gapped system. Our correlation should be very, very small, and okay, and this is, we start with a very simple system where your nearest neighbor are strong J1, J prime is your next, I mean the exchange interaction between the 2 trimers, and today we'll be just focusing on the both antiferromagnetic. Your J and J prime both are antiferromagnetic in nature, although you can consider ferromagnetic, but that gives you more complex excitations. Okay, so again we do the similar kind of analysis. We take the three spins, like a three spin one, and how many degree of freedom you have? 3 to the power 3, 27, right? And in fact, you can write a very simple transformation of this Hamiltonian, and energy can be written in terms of the total spin, which is 1, 2, 3 is the total spin of the system, and in terms of 1, 3 and spin 2. And here is the table for all the possible energy you can have. So your ground state, which is minus 3J, again your total spin is going to be 1, and you know that it should be threefold degenerate, right? And you can see that way that how many possibilities you can have, what kind of a spin you can form. You can form the spin from 0 to 3. That's the maximum. 3 can be the maximum spin, right? S3 is the total like this thing, and that is which is highest in energy here, and that's a 7-fold degenerate, right? And because 2s plus 1, that's the multiplicity you have. And based on this, you can again name the same nomenclature you can use, that if you have like if it's a ground state, in ground state you have this spin 1 as a effective spin of this trimers, so that's fine. But if next excitation is 0 spin, and you have only one simple one ground like a state, one fold, there's no degeneracy there, so it's only one particular state. So that's why you call it singleton, right? And if it is again one excited state, then you can say tripleton. If it is 2, you can say penton, and keep going on. If you have 7-fold degeneracy, you can say the hepton. Okay. Once these are isolated trimers, then you can define it. But what you can do is like you connect it now with the exchange. And now it's no longer the discrete energy levels, rather it is forming a band. And you'll have a magnon band, singleton band, tripleton band, penton band, and so on, right? And actually in weak coupling limit, you can do the perturbation theory. Let's do the first order perturbation theory. And what you find here is that your effective spin is again spin 1, because your ground state spin of the trimer was 1. And this J effective will turn out to be 9 by J prime by this one, okay? And you know that results would be very similar. So basically your low energy physics will be still dominated by the spin 1. Only thing is the length of the chain has now is different, because each of the 3 spin is equivalent to 1 spin now, right? And this is what we get if you have G1 is equal to, so it's a uniform chain if you take it. That's how your dynamic structure factor should look like, okay? So you see that here at the Jones boundary, you will have the large gap. That's what is the Halden gap, okay? And then here you will have the 2 magnon excitations and so on. Okay, this is well known, so I don't have to do anything. I just try to reproduce it, whether our calculations are correct or not. Okay, but once you have this J prime different, let's say very small, okay, then you expect this, all the confinement effect should be coming, right? You see the low energy physics is again governed by your effective spin 1 chain, right? That's what we did it for perturbation, using the perturbation theory, and that's what you see. Only thing now your like a Brilliant-Jones has shrunk to this right, and at this point pi by 3 is now your actual Jones boundaries, and that's where the Halden gap you should look for. And actually, if you see it, zoom it, then you find that your Halden gap is proportional to J effective. Okay, 4.1, that's a well-known number, what Halden and other people calculated. And the bandwidth is proportional to your J prime. Okay, and that's your low energy physics. But if you keep going here, these are actually singleton and tripleton bands. These excitations are now coming because of the excitation within the trimers. These are not extended like a states trimer, although these will be weakly dispersing, but there's a broadening here, so that tells you that there is a very weak like a dispersion in that, but it's almost flat. So I would assume that these are localized states. Okay. Similarly, you'll have the C and D. I forgot the nomenclature, but I think it should be penton bands. Okay. So what happens when you are trying to increase the J prime? Okay, intertrimer exchange, and then you find that if this ratio is 0.2, you are in weak coupling limit and these bands are well separated. As you keep increasing, you see that slightly this person is increasing in these states. By the time you're 0.5, these two upper bands, singleton and tripleton and penton bands, are now started mixing. Okay, and this is also trying to vanish slowly, the lower well-known dispersion relation. But by the time you are 0.8, now you see that it started behaving as if it is a completely mixed system and behaving as if it's a full spin chain. And then finally you are at spin 1. Okay, so how do you understand this? So you understand that these low-lying magnetic states, you know that this happens because of the breaking of this BBS state. But as you go for the singleton excitation, these are no more because of the breaking of the BBS state. Rather, these are coming from the internal excitations of these trimers. Okay, so in singleton excitations within the trimer, what you do is like to adjacent singlet you break it. Okay, similarly for tripleton excitations, you keep breaking this singlet bonds within the trimers and effectively maintaining that your spin should be 1. Because if you see the wave function in the table I showed, you'll see that there are lots of let me go back. You see here, these are singlet pair it is forming, and these are spin 1 singlet pair, not spin half pairs. Okay, and if I have mentioned this, if it is a square, then that represents your triplet state formation. Okay, so they break this and then goes to the higher excitation. Those are the internal excitations of these trimers. Okay. Yes, 5 minutes, I'm almost done. Okay, so that's how this tripleton excitation and penton excitations are there. So these are just manipulation of these your singlet and triplet states and giving you the effective spin either 1 or 2 depending on what kind of excitations you have. Okay, so now our question is, are there any materials which exist and gives you this trimer spin 1? I would say, fortunately, there are a few compounds from our Indian group, Mayuk and Anup, both have designed. And I would say the problem with this material is that these are highly connected chains. So we cannot say that these are the real material, but they are trying to form this, that effectively they are J2 is weaker, and then they have J3, which is culprit. We don't want J3. Similarly, there are groups from Japan, and also they are forming this particular compound. Unfortunate thing about this is that these are again effectively behaving as spin 1, but because of this mixed valency, there will be spin fluctuations. Okay. So I think my time is over, so I'll just wrap up. And with this, we have done this. We have studied this spin 1 trimer, and I showed you that there's a weak in this. We consider a chain where we have the weak coupling between the intertrimer states, and you can create various kind of excitations like Magnon excitation, singleton, tripleton, penton, and hepton kind of excitations you can do, and these can be observed using the inelastic neutron scattering. And in this particular limit, you know that it's going to be chain, and you should be expecting similar excitation. Thank you. And this is group, and they have. Okay. Thank you.
Yeah.
Yeah.
Maybe I can talk. Backside, nobody will hear. That's better to use the microphone.
Uh-huh.
So, thank you very much. So, I think in the last, before the last slide, you showed the calcium-based, nickel-based system, and also the system of manganese-based system, which is likely to be the spin trimer. Things could be happen, right?
Yeah.
So, is there any investigation has been performed on these two systems, in particular the first one?
No, not really.
Okay.
Not really.
So this is just a theoretical proposition still,
Theoretical,
right?
I mean, they claim that, okay, because you see that why this is trimer is this one, right? The distances, if you see, these are very close by, so that's what this should be trimer. Only thing that valency fluctuation is there, so then there's a problem, right?
Yeah.
Even if it's forming trimer, it is not the material we're looking for.
Yeah, so but in these two systems, I'm just continuing here. So in these two systems, so essentially the spins are much more localized, I guess, right?
Low energy, I would say not really, because you see that if it's the effective spin 1, it will start behaving as if there's a effective, the 3 spins merge into spin 1,
Okay.
and then this is getting delocalized.
Okay.
Yeah.
Thank you very much.
Thanks.
So I just want to ask you, treating this J dash not as perturbatively if it's really strong. Okay. So your perturbation whole calculation goes wrong then. How to treat then if J dash is really strong?
DMRG. That's where all the calculations are. This is effective. We have done it to understand the low-lying physics, right? I mean, when J prime is very small. But if it is very strong, you have to do the DMRG or that kind of calculation. There's no way other out. There's no way out. Right?
Okay, thank you.
Have you done it classical?
Why you want to do classical? Classically, there's nothing like this. This classical system will be all continuous, no discrete excitations.
Yeah, but classical phase diagram is intuitive.
There's no phase diagram here. I mean, classical one is spin half, doesn't matter. All are gapless.
And how does the trimer system tend to be in spin 1 total?
So you're saying
Why they don't behave as independent spins?
Because there is exchange. No? You see this calculation. If you do it, you're saying that if you put the J is equal to 0, all are individual spin independent. Like once you put it, it should follow. It should minimize the energy, right? And the minimum energy is when you have the spin 1. And you see, this will be your wave function, one of your wave function. Yeah.
What are the typical energy transfers involved in the inelastic scattering?
Okay, so in this one, and that will depend on your J, right? So if you see, this is what you have, like in milli electron volt. Yeah. Yeah, Anup Ji.
Have you found the magnetism plateau for the spin 1? How many plateaus?
It should be.
It should be.
It
Have
should.
you looked on that?
Not yet, but I mean that's guaranteed.
Like spin half you are getting on.
It's a guaranteed.
Yeah.
Yeah.
Anyone else? Okay, Manoranjan.
Thank you.